Now, proceeding from the previous lecture where we had obtained the hybrid parameters for a general linear circuit, and if I go back exactly in that linear device where we had a linear network with two inputs and two outputs, and we obtained two important equations. One was V1, that is H1 I1 for any linear circuit, plus HR V2. And we have I2 equal to HF I1 plus HO V2. So we have this set of equations for any linear device, say transistor in our case, right? So we have two inputs, right? We have V1, I1, and we have V2 and I2. And now, what am I trying to say here is that if we look on this equation, say I'll call this for the sake of argument as equation 1 and equation 2. Now, equation one is basically it is the sum of two voltages. So in the left hand side I have the voltage. Certainly I must have voltage in the right hand side. So it's the sum of the two voltages. The voltage across the impedance and due to the current I1, due to the current I1, and voltage HR V2. This is another voltage, right? This is transferred from the output into the input. Now this equation that we have here, the equation of voltages. This we can draw as an equivalent form. We try to do that. So what I have is I have an impedance, right? And I have a voltage generator here. So this is my HI. All right. So what is this? This is HR. HR from what? V2. Okay. And say this is plus and this is minus, and let's come back like this. So here I have the input, say V1. So V1 is HI I1, right? So here I have the current I1. Okay, so this is HI I1. Then we have a voltage generator as HR V2. So this is basically the hybrid equivalent of equation 1. This is hybrid equivalent of equation 1. Okay. Now, what would we try to do is now we would like to have a hybrid equivalent of this equation, and we can understand that this equation has current in the left hand side. So overall we have current here, and here we must have the reciprocal of current in order to get current. Right? So this is the equation of currents, and this is the equation of voltages. Now to move forward, so now let's try to draw this this equation, the equivalent circuit for this equation. Right? Now, in order to do that, we have to have a current generator, right? And we have to have the reciprocal. So this is my HO, and I will have here what I will obtain is the output. So here I will have V2, right? So this is my V2, and this must be HF. This is forward current gain, and this must be my I1. And here can have I2. Okay. So what we have here is that we have here the sum of the sum of two currents. So I2 is the sum of two currents through the admittance. This is my admittance due to the voltage V2, right? And the current uh, HF HFI1 is transferred. Basically, it's transferred from the input into the output. It's transferred from the input into the output. Now, this is basically represented by this equivalent circuit. So this is an equivalent circuit for this equation I2, and this is the equivalent circuit for this equation, what's called as V1, voltage equation and current equation. Now, by measuring the H parameters, the H values for a transistor, I mean, this circuit may be used to replace the transistor in the circuit analysis. No matter whatever is the configuration, I mean, no matter whether we have common base, common emitter, or common collector amplifiers to be considered, the same equivalent circuit configuration can be used as long as we make use of appropriate numerical values for the H parameters that are involved in those transistor configurations, right? Now, these equations and these equivalent circuits, these set of two equations and these equivalent circuits that we have here for the input circuit and for the output circuit, they hold for NPN transistors and PNP transistors, whether you have from germanium or you have from silicon at low frequencies. Right? Now, if we generalize this thing, if we move on from here, so we have the equivalent circuit for the equation 1, and we have the equivalent circuit for equation 2, and we can replace a transistor by these two equivalent circuits, and we can analyze the circuit and can have the results to be obtained in a very, very simplistic way. Now, if we take the common emitter configuration, now if we go with the common emitter configuration of an amplifier, suppose I have an NPN transistor like this, and it has the collector current, it has the load resistance, it has the voltage, okay, in the output circuit, and this is its emitter, and the input is to be given at the base of this transistor, and we have Vs, we have signal voltage here involved, and we have the biasing battery here to make this input forward biased and output reverse biased. And this is my emitter, and this is my base. So here I have base current, and I assume that this is Rs, that is signal resistance. And here I have collector current, and this is RL. And this is the VCC, and this is VBB. All right. Now, if when I consider this NPN common emitter configuration of a transistor, the input signal you can see is applied between base and the emitter, and the output signal is drawn between the collector and the emitter. Okay, and this RS, it is the resistance of AC source that we are using here. This RS is the resistance of this AC source, and this RL is the resistance of the load, right? The emitter is has to be the forward biased, and we can see the biasing is absolutely fine for the input circuit to be forward biased, and this output circuit should also be reverse biased, and we can see the biasing is such that the output circuit of this common emitter configuration is reverse biased. So what am I trying to say here is that the values of this RL or VCC and VBB, they ought to be chosen such that the quiescent point, or what we call as operating point, is approximately in the center of the linear region of the input characteristics. Now this is not input characteristics, probably output characteristics, right? So this is done to minimize the non-linear distortion in the output. Okay, as the case may be, we have to set this RL, this VCC and VBB. We have to be set in such a way so that the Q point, if we consider here as input circuit, in that case we have to choose the linear portion so that the fluctuations that we can have in the output circuit can be minimized, so that there is no non-linear distortion in the output, and the amplifier action is based on the principle that we understand that a small change in the base current due to input signal produces the large change in the collector current, which is basically responsible for amplifying action of a common emitter transistor. Now, what am I trying to do here is that what we are supposed to do, what we want is we want the input resistance. We want to determine the input resistance, the voltage gain, the current gain, the power gain, with the aid of these equivalent circuits with load resistance. So we will have equivalent resistance with load resistance, and we will have an equivalent circuit. So here load resistance without RS, signal resistance, and we will have another equivalent circuit with signal resistance, but without load resistance. Now, in order to have those two equivalent circuits, I would like to draw the equivalent circuit with RL and without RS for this whole configuration. So if I start here for without, let me use the RL, but I will not use RS. So what should I do for that? I have HIE, then I have voltage generator. So this is HRE for common emitter configuration. This is VCE. Okay, and here I will have VB, and then the output circuit will be like current generator here, and here I will have admittance. Okay, and this admittance is that has to be here as the resistance. So this will be my load resistance RL, and this will be 1 by HOE. Okay, and here we will have, if it is visible, I don't know, I'm not sure. here we will have the collector voltage VC, and here as input we will have input voltage VB. Now this is an equivalent circuit. This is the hybrid equivalent circuit for the common emitter configuration of a transistor when I consider the load resistance RL and I'm not considering the signal resistance. So what would I do? I would like to draw another equivalent circuit in which I will remove the load resistance and I will remove the load resistance and I will use the signal resistance only. So here we can write, this is my IB in this case, this is HIE, this is HRE, this is 1 by HOE, this is RL here, and after this we have VC, that is the output voltage. Now to have now let me consider this the H equivalent for this circuit, assuming there is no RL but there is VS. So to do that, yeah, how would it come like? Here is I will have this is my HIE. Right here I will have HRE, as is the case. This is HRE VCE. Okay, so here is a voltage generator, and this will give me what? This is RS. This is this RS. Okay, RS times the current will give me, it will give me VS, right? So this is RS here, so this is VB. Okay, then I will have an output equivalent in terms of a current generator. Okay, then I will have the admittance, that is 1 by HOE. Okay, and then here what I will have is collector voltage. Okay, it should be like this. Now we can see in this circuit we don't have the load resistance, and instead of load resistance what we have the resistance of the source. Now if we compare the two, this is the equivalent circuit, this is the H equivalent circuit for this common emitter configuration of this transistor. When I consider the load resistance and the resistance of the signal is not considered, right? For that we have this equivalent circuit, and similarly for a situation where I don't consider the load resistance and I only consider the resistance of the signal, for that we have this as the equivalent circuit. Now after this, in our next video we would like to do the mathematical analysis of these H parameters, where we'll use these H parameters. We'll obtain certain things like input resistance, the voltage gain, the current gain, the power gain, with the aid of these equivalent circuits and with the aid of these H parameters that will be involved in these situations.